Okay, so today we're going to be looking at, we're starting a new unit, weathering and erosion, and what we're looking at is the topic of weathering. All right, so weathering and erosion are two processes that people frequently get mixed up. They look at something and say, oh, that's undergone erosion when it's actually undergone weathering, or vice versa. Now, both these processes are related to each other, but they're completely separate processes, though. So today we're going to focus on what is weathering, what are the types of weathering, and what are some of the things that affect how much weathering takes place. So first off, what is weathering? Weathering is a breaking down of rock material. All right, so as time goes by, rocks, when they form, are typically large masses. As time goes by, they gradually break down into smaller pieces. And that process where they break down is what weathering is. Now, there's more than one way in which they can break down. One way they can break down is where they just go from big parts to small parts. All right, so it's the same, basically it's the same rock, it's just smaller pieces of the same rock. And that process is called physical weathering, or sometimes called mechanical weathering too. So the chemical characteristics are exactly the same, it's just smaller pieces of something that used to be big. All right, now, different types of physical weathering. All right, well, first off, give you an example. So let's say right here, I have a lifesaver. All right. I am going to physically weather this lifesaver. All right, so what I have is something that was pretty big at one point, is now just broken down into a bunch of smaller pieces. Now, if I were to taste those pieces, they're all going to taste the same, but they're just smaller pieces of the same thing. All right. So that's what physical weathering is. All right, now, in nature, most physical weathering is not caused by guys with geology hammers busting on things, but there are some things that act kind of the way that the hammer does. And one of those things is the process of abrasion. All right, so what abrasion basically is when rocks collide in with each other. All right, so like these two rocks right here, all right, if these two rocks banged into each other, what would happen is little pieces of the rocks would break off. That would be physical weathering. All right. Now, in nature, where am I going to have rocks bang into each other like that? Well, I could have them bang into each other with an avalanche, as the rocks are kind of rolling down the side of a hill, they could bang into each other, little pieces break off. But more commonly, where you're going to find this take place is with moving water, for example, at the bottom of the stream. So, like if this tray right here was the bottom of the stream, what would happen is like if the water was flowing this way, it might cause this rock to move and then bang. It bangs into that rock right there, breaking off little pieces of it and resulting in physical weathering. So rocks banging into each other's abrasion. Another place that can happen besides either the bottom of a stream or like the beach, you can also have wind abrasion. That takes place where you see the most effects of that would be like in a desert. Where the wind's blowing really fast, it might pick up little grains of sand, and then the little grains of sand will bang into each other, or the little grains of sand might bang into rocks that are on the ground or something like that. So you can get abrasion with wind too, but most abrasion is a result of water. Okay, next, type of physical weathering. All right, now, imagine it's a really hot day outside and you're playing little hoops. You come inside and you're all really thirsty and you open up the refrigerator and there's nothing to drink. Your mom comes home from the grocery store and she bought some soda, but it's been sitting in the car for a little while, so the soda's all warm. It's kind of gross. So you want to cool down that soda. So what you can do is you say, I'll put this in the freezer for a little while and let it cool down. So you put that can of soda in the freezer and you're going to go back and check on it, but then you find something else to drink and you forget about that can of soda you put in the freezer. You go back a few hours later and you check on that soda, and what you might end up finding is a can that looks something like this. All right. So if you notice here, the top of that can right there has been busted out. All right, it's bulging upward and it's kind of busted out. There's a hole there now. That's where the soda came out. If I look at the bottom of the can, it's now bulging outward like that, whereas the bottom soda cans normally are going to bend inward. This one bulges outward. So this can can't stay up. It rolls off like that. All right. Now the reason why that happened is because when water freezes, it expands. And when it expands, it expands with a tremendous amount of force. As a result, it pushed out the ends of the can. All right. So it takes a tremendous amount of force to do that to the soda can. Well, same thing happens with water when it gets into rocks. So what will happen is, like, you have a rock like this, and there may be a little crack in it like that, and what will happen is water will get in there and fill in that crack, but then when the water freezes, water expands when it freezes, so that ice right there is going to expand, and it's going to cause it to go outward like that. It's going to expand that way, and that's going to cause that crack to get a lot deeper, right? Now, what's also going to happen is when that melts, that water can now penetrate even farther down, so more water can get in there. And then if that liquid water freezes, this will expand even more, and what will end up happening is it ends up breaking the rock in two pieces, right? So that process is frost action. If you live in a cold, humid climate where you have colder temperatures and lots of water, you get lots of frost action. Now, what's going to cause the frost action is every time that water freezes, right? So the more time the water freezes, the more frost action you get. As a result, you probably get more frost action in a climate like upstate New York than you would at the South Pole. And the reason being, in upstate New York, you have lots of days where it gets above freezing, then maybe it gets like 45 during the day, then 25 at night, 38 during the day, 27 at night, Fahrenheit. So it keeps fluctuating above and below the freezing temperature. And every time it refreezes, you get frost action tearing the rock apart. Whereas if at the South Pole, where it might be minus 70, all winter long, you don't get that constant freeze thaw, which breaks the rock apart. So you're most likely going to get a lot of frost action in a situation in a climate where the temperature is going to fluctuate above and below the freezing temperature. All right, next, root action. Plants' roots breaking rocks apart. All right. So what happens here is, let's say I have a rock like that, and there's a little tiny crack in that rock, and there's a plant, and the plant has some roots. Right? And let's see when the roots gets down into that little crack. Now, as the plant grows bigger. The roots will get longer, but what also happens is the roots will get thicker. All right? And when that root grows, it's already in that crack. When that root grows, it's going to start prying the rock apart. So just like ice when it freezes was prying the rock apart, as the width of that root starts to grow, it's going to start prying the rock apart. So maybe the crack becomes that big now. All right? This plant gets bigger yet. The roots get longer. but they also get wider. Oops. Well, that guy there is going to get wider too, and eventually it will end up breaking the rock apart. All right. So that's the process of root action. And a good example of that is this picture right here. All right, if you ever wondered how paper beats rock. All right, so what happened here is apparently a seed or something got down into the crack of a rock, and as that seed grew for this tree and it got bigger, as it grew, it pried the rock apart. So this big giant boulder is being pried apart by that tree. So that'd be an example of root action too. All right. So these are all types of physical weathering. I'm just taking something big and breaking it down into something small. All right. Chemical weathering is when the rock breaks down, but the chemical composition of that rock is changing. Right? So chemical weathering, changing a rock's chemical composition when exposed to water, which is the hydrosphere part of the earth, or air, the atmosphere. Right? Now, there's different types of chemical weathering. Dissolving is one of them. So just like, all right, get a little bit of water here. All right, so that lifesaver that I smashed up, those lifesaver pieces I just smashed up a few minutes ago, take that and I put that in water and I start to stir it. What will happen as time goes by is those little pieces of lifesaver look like they're disappearing, all right? And if I stir this enough, what I'll end up with is something like that. So the lifesaver, that's the lifesaver now, right? The lifesaver chemically became part of that water. Right? That is a process of dissolving. All right, that's dissolving. Now, that's just a piece of candy. You might be like, oh, rock can't be like that. Well, yeah, there are some types of rock that dissolve just as easily as that lifesaver did, and most notably rock salt. All right, rock salt, the stuff they sprinkle on the icy roads and icy sidewalks, is a rock. I mean, there's places in central New York where they mine rock salt. There's several. There's a rock salt mine in Ithaca. There's a rock salt mine in Watkins Glen. There's a rock salt mine near Geneseo, where people go down several hundred feet underground and they toil in the salt mines to bring you salt so you can put on the roads and so forth. So that's a rock that dissolves very easily in water. Some other rocks dissolve in water too, just not as fast as rock salt does. Like limestone can dissolve in water too, but much more slowly. So some rocks dissolve in water, other rocks dissolve in acid. All right? And limestone is the most obvious example of that. And I could demonstrate that. I have a nice piece of limestone up here. All right, so I have a little container full of acid. Got my safety goggles on, because safety first. I got my acid right there. And I have a piece of limestone. What I'm going to do is take a little bit of the acid and put it on the limestone. And what you will see it bubbling like that. You hear it too? That is the rock dissolving in acid. That is the rock dissolving in acid. Now that's a really strong acid, so that dissolves the rock very quickly. In nature, you don't normally find acids that strong, but weaker acids do the same thing. It just takes a lot more time for that to happen. And weak acids are very common. Rainwater is slightly acidic, so rainwater can eat away at limestone. It just takes a lot longer because it's only slightly acidic in most cases. All right, so that's dissolving. Another type of chemical weathering, oxidizing, right? Our atmosphere is made mostly of nitrogen, which really doesn't do too much, and oxygen, right? That oxygen can combine with stuff like iron and make rust, which kind of deteriorates the rock. If you've ever seen pictures like the Grand Canyon and you see the rocks there kind of have an orange, reddish look to them, that's because the rocks have iron in them that's combined with oxygen. So basically the rocks are kind of rusty there. So rocks can undergo oxidation as well, or rusting as well. Now, some of the things that affect weathering. All right, well, one thing that affects weathering is climate, right? In a hot, humid climate, so think of maybe like Florida, all right? The type of weathering that's most dominant there is chemical weathering. And the reason being is, chemical weathering uses water, but also warm water dissolves stuff faster than cold water does. If you have like a coffee and an iced coffee, and you try dissolving some sugar in both of those, it'll dissolve really quick in the hot coffee, but it takes a long time to dissolve in the cold coffee. So in a warm, wet climate, rocks dissolve much more easily than a cold, wet climate. So chemical weathering takes place the best in hot, humid climates. In a cold, humid climate, physical weathering is dominant, and the reason for that, if I got cold temperatures in water give me frost action. So cold, humid climates have lots of frost action, therefore there's lots of physical weathering. Dry climates. Now it doesn't matter if it's cold and dry or warm and dry. Dry climates, you don't get very much weathering at all. And the reason being, well, if you look at most of these types of weathering, most of these involve water. I mean, root action. Well, plants need water. No water, no plants. No plants, no root action. Frost action, well, ice is just frozen water, so no water, no ice. Abrasion, all right? We said earlier that most abrasion takes place from moving water with the rocks banging into each other. You can get abrasion with wind, so there are, in deserts, you do get some abrasion with wind, but usually most abrasion is a result of moving water, so you're not going to get too much abrasion. You're not going to get dissolving really, because dissolving usually uses water and so forth. So since most types of weathering involve water, if you don't have the water, you're not going to have very much weathering. So that's why things last a really long time in dry climates. A lot of the things like the ancient pyramids and the Egyptian pyramids and so forth. Some people are like, oh, they must have had some, super technology back thousands of years ago that we don't understand. No, we understand it. They did a good job building the pyramids, but the reason why they're still around largely is because the Egyptian area is dry and things last a long time in dry climates. You take a lot of those Egyptian features and you move those into a humid climate, they're not going to last that long. And there's actually, I think 100 years ago, there was this this ancient Egyptian thing called Cleopatra's Needle. It's like a big obelisk thing. It was in Egypt. It was several thousand years old, and it had all sorts of hieroglyphics and stuff on the side of it. And they're like, oh, this would be a really cool thing to move to London in New York City. There's more than one. Anyways, they moved to a humid climate. Well, the thing lasted for thousands of years in the Egyptian desert, but once you moved it to a humid climate, they found in just a matter of decades that a lot of these writings on the side of the obelisk were starting to wear off, all right? And the reason being is because in a humid climate, the rocks don't last that long. In a dry climate, there's not much weathering, so it lasts a really long time. So in dry climates, you don't get very much weathering. Composition, different materials weather at different rates. All right, well, some rocks are harder than other rocks. So if I have a hard rock and a softer rock bang into each other, the softer rock will break into pieces more than the harder rock will. All right? So different materials weather at different rates. Or with rock salt, all right, rock salt compared to like granite. All right, well, rock salt, you know, it's not that soft, but it is very susceptible to dissolving, right? And the reason why rock salt dissolves and granite doesn't is, again, the chemical composition of it. So different materials weather at different rates. 3, exposure. The more the rock's exposed, the more weathering takes place, all right? So let's say I had 2 identical rocks. One of them I left at the surface. The other one I dug like a 30-foot hole, dropped it in there, and then buried it. And I came back 60 years later and I checked out those 2 rocks. The one at the surface, and then I looked at the one that was buried underground. What I'm probably going to find is the one at the surface would have gone through a lot more weathering than the one I buried underground, because the one at the surface is going to be the one that's going to be exposed to like water, changes in temperature, the sun, plants. You might have like algae growing on it or lichens growing on it, where the one buried underground is going to have to deal with all that. So because one was exposed to the elements, it's probably going to undergo a lot more weathering than the one that was buried safely underground. So the more rocks exposed, more weathering takes place. Lastly, particle size. All right, small particles weather faster, more surface area. All right, so I'm going to another demonstration here with lifesavers. All right. So I'm going to take one, I'm going to smash it again. Okay, so one of them smashed, the other one's whole. I'm going to take the whole one out. Take the smashed one. All right. All right, so I got a whole one, and I got the smashed one. I'm putting both of them out at the same time. I'm gonna suck on them. All right. Oh, what's happening? All right. Here's the one lifesaver. Here is the other lifesaver. All right, broken up into pieces. Now, as I'm sucking on the lifesavers, saliva is dissolving them. All right. Now, they're not dissolving at the same rate though. On this one, my saliva is working right there and right there. Well, on this one, my saliva is working right there, right there. It's also working right there, 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 right there. There's a lot more surfaces for my saliva to dissolve, to work on that lifesaver. Now, the more I smash this into smaller pieces, the more surfaces there are to get dissolved. So like right now, between those 2 lifesavers, one of them's already gone, but the other one is still largely intact. All right. The full one's still largely intact because there's not very much surface area. As a result, it's taking a lot longer to dissolve. Where the one that's broken into pieces, there's a lot more surface area to dissolve quite quickly. So, moral of the story is when you have a really big giant boulder, it takes a really long time for that big boulder to break into like a couple pieces. But once it starts to break into smaller pieces, the rate at which it weathers just gets faster and faster and faster, because every single time it breaks to a smaller piece, there's that much more surface area to weather, and it breaks down even more and more and more and more and more and more. So the rate of weathering increases as a rock breaks into smaller pieces because the surface area increases. All right, so that is weathering, physical weathering, chemical weathering, and the factors that affect how much weathering takes place.